Use Green's theorem to evaluate the integral over c of f dot dr. Check the orientation of the curve before applying the theorem. Our force field f of xy is given by the vector function e to the x plus x squared y, comma e to the y minus xy squared, and c is the circle x squared plus y squared equals 25 oriented clockwise. And so you can see we have the wrong orientation to use Green's theorem initially. We have this circle of radius 5 centered at the origin. So it looks something like that. Radius on it is 5, but it's oriented clockwise, meaning we're traveling in this direction. That's a negative orientation. We want a positive orientation. In fact, we have to have a positive orientation to use Green's theorem. So if I take the integral over c of f dot dr, where c is this orientation, clockwise orientation around this circle, well, then I can switch the orientation by negating that integral. I can take the negative of the integral over negative c of f dot dr, where negative c is the same curve, only with the opposite orientation. This will be a positive orientation traveling counterclockwise around that circle. And so this is the integral that we can use Green's theorem, because this is the integral over a curve, a closed curve with positive orientation. And so by Green's theorem, this is equal to the double integral over the region that's enclosed by this circle. We'll call that D. And let me go ahead and shade in. That's just obviously the area inside this circle. And so this region here, D, on or inside this circle, is what we're going to integrate over according to Green's theorem to get this line integral. So again, we call that D, and we're going to integrate then. Green's theorem says we integrate the partial of our second component function with respect to x. So we're going to take the partial of e to the y minus xy squared with respect to x minus the partial with respect to y of the first component function, what we sometimes call p. So that's going to be the partial with respect to y of e to the x plus x squared y, integrating all this dA, A being the area of that domain D. So this is equal to the negative of the double integral of, let's see, the partial with respect to x here is going to be just a negative y squared. And the partial with respect to y is just going to be, well, let's see, that'll be 0 plus x squared. So with this negative here, it'll be a minus x squared. Now, we're integrating over a circle, so I think we should switch to polar. I hope you agree. That'll change our dA to an r dr d theta, and r is going, of course, from 0 to 5. Theta going around this circle counterclockwise, so from 0 to 2 pi. So I'm going to take a negative out of the function that I'm integrating here. Factor a negative out of the negative y squared minus x squared. That'll make my overall double integral positive from 0 to 5, 0 to 2 pi. And of course, when we convert to polar, x squared plus y squared is the same as r squared. So I have r squared r dr d theta. And so the double integral from 0 to pi on the outside, 0 to 5 on the inside, r to the third dr d theta. So let's go ahead and integrate them with respect to r. That's r to the fourth over 4. And that's going from 0 to 5. And then we'll integrate that result with respect to theta. And let's see, 5 to the fourth is 625. So I have 625 over 4 minus 0. That's our integral. 0 to 2 pi d theta. And so we just get 625 over 4 times 2 pi. And so that will simplify then to 625 times pi over 2. So that is the value of that line integral. We use Green's theorem to get it.